In this episode, we're going to make confidence intervals feel like a practical tool for thinking, not a confusing math artifact that people repeat incorrectly. Beginners often see a confidence interval as a fancy way to say a number plus or minus something. And while that is not totally wrong, it misses the deeper point. A confidence interval is a way to describe uncertainty around an estimate, especially when that estimate came from a sample rather than from a complete population. In data work, you are almost always working with samples, even when the sample is large, because you rarely observe every possible case. The CompTIA Data AI exam will likely test whether you can interpret confidence intervals in a careful, correct way, because many people use them in sloppy ways that sound confident but are logically wrong. The goal today is to help you understand what a confidence interval is actually saying, what it is not saying, and how to avoid the classic traps that make smart students lose easy points. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start with the core idea that an estimate is not a fact about the universe. It is a value computed from data you happen to observe. If you collect a different sample, your estimate will generally change, sometimes a little, sometimes a lot. A confidence interval is designed to capture that sampling variability by producing a range of plausible values for the true unknown quantity, like a population mean or a difference between means. The interval is built using a method that has a long-run reliability property, meaning that if you repeat the same sampling process over and over, a certain percentage of the intervals you compute would contain the true value. This is the part that beginners usually skip, but it is the part that makes the concept precise. The interval is not claiming the true value is random in a mystical way. It is acknowledging that the interval is random because it depends on the random sample. When you treat the interval as a product of a procedure rather than a magical statement, the correct interpretation becomes easier. Now let's address the most common misunderstanding directly, because it shows up everywhere, including in exam answer choices. A 95% confidence interval does not mean there is a 95% probability that the true value lies within this particular interval. That statement sounds reasonable, but it is not what the traditional confidence interval framework means. In the usual interpretation, the true value is fixed and unknown, and the interval you computed is the thing that varies from sample to sample. The 95% refers to the method's long-run success rate, not to a probability assigned to the true value after you have computed one specific interval. Once you compute an interval, it either contains the true value or it does not, even though you do not know which. The confidence level is about how often the method would succeed over repeated sampling, not about the probability of success in this one case. This is subtle at first, but it is exactly the kind of subtlety exams like to test. A useful way to make this feel intuitive is to imagine running the same experiment many times, each time collecting a new sample and building a new interval the same way. Some intervals will land higher, some lower, because the sample fluctuates. If the method is a 95% confidence method, then over a long run, about 95% of those intervals would cover the true value. The confidence label is attached to the method, not to a single interval taken alone. This perspective also helps you understand why a single interval can be misleading if you treat it as a guarantee. A wide interval is telling you your estimate is uncertain, while a narrow interval suggests the estimate is more precise, but neither one is an absolute promise. The point is that confidence intervals are honest about uncertainty, not magical shields against being wrong. When you interpret them this way, you stop overclaiming and start reasoning responsibly. Next, let's talk about why intervals have width, because width is where most practical meaning lives. The width of a confidence interval reflects how much uncertainty is present in your estimate, and that uncertainty is influenced by sample size and variability. When sample size increases, intervals tend to get narrower because your estimate becomes more stable across repeated samples. When variability in the data is high, intervals tend to get wider because noise makes it harder to pin down the true value. This is a key connection for the exam, because you might be asked what happens to a confidence interval when you collect more data or when the data becomes noisier. The correct answer usually involves precision, not correctness, because collecting more data does not guarantee your estimate becomes closer to the truth in one specific sample, but it does improve the expected precision of the estimation process. Beginners sometimes think more data always shifts the center of the interval toward the truth, but the more accurate statement is that it reduces the typical spread of estimates around the truth. Precision improves, not destiny. Confidence level also affects width, and this is another place where the exam may test your intuition. If you increase the confidence level, like going from 95% to 99%, you usually get a wider interval, because you are asking the method to capture the true value more often. A wider interval is the price you pay for more coverage. If you decrease the confidence level, you usually get a narrower interval, because you are accepting a higher chance that the interval misses the true value. Beginners sometimes think higher confidence means a tighter range, but it usually means the opposite. This makes sense if you think about catching a moving target. If you want to catch it more often, you cast a wider net. On test questions, distractors often exploit this confusion, so it is worth locking in the correct direction now. Higher confidence generally means wider intervals, and lower confidence generally means narrower intervals, all else equal. Another critical interpretation skill is understanding what it means when a confidence interval includes a particular value, especially in comparisons and hypothesis testing contexts. If you have an interval for a difference between two means, and that interval includes 0, that suggests the data is compatible with no difference at the chosen confidence level. If the interval does not include 0, that suggests the data is compatible with a non-zero difference, and it often aligns with a statistically significant result at a related threshold. This connection is common on exams because it lets you reason about significance without explicitly doing a hypothesis test. Similarly, if you have an interval for a ratio and it includes 1, that can suggest no effect in ratio terms. The key is to know what value represents no effect for the parameter you are estimating. Beginners sometimes misapply this by checking the wrong baseline value or forgetting what the interval is actually about. Always identify the parameter, like difference or ratio, then identify the no-effect value for that parameter, then see whether the interval crosses it. A classic trap is treating confidence intervals as if they are statements about individual observations rather than about an underlying parameter. A confidence interval around a mean is about where the true population mean might be, not about where future data points will land. Individual observations can vary much more widely than the mean, especially in noisy datasets. This is why you can have a narrow confidence interval for a mean while still observing values that are far away from the mean. Beginners often see a narrow interval and assume future outcomes will be tightly clustered in that range, which is a misunderstanding. Predicting future observations requires a different kind of interval that accounts for both parameter uncertainty and observation level variability. Even if you have not learned those intervals formally, the exam may still test whether you can fuse the two ideas. A safe habit is to remember that confidence intervals talk about uncertainty in an estimate of a parameter, not about the spread of individual data points. Another interpretation trap involves overlap between confidence intervals, especially when comparing groups. People sometimes claim that if two confidence intervals overlap, there is no significant difference, and if they do not overlap, there is a significant difference. This rule of thumb can be misleading because the relationship between overlap and significance depends on how the intervals are constructed and what exactly is being compared. Overlap does not automatically mean no difference, and non-overlap is a stronger signal, but still not the full story. A more reliable approach is to focus on an interval for the difference directly, because that interval answers the comparison question more directly. Exam questions may include a distractor that tries to get you to use the overlap shortcut as a law, and your job is to be cautious. You can say that lack of overlap suggests a difference, but you should not treat overlap as proof of no difference. Confidence intervals are evidence tools, not yes or no stamps. You should also watch out for the misconception that a confidence interval is only about randomness and ignores bias. If your data collection or measurement process is biased, you can have a very narrow confidence interval around a biased estimate. The interval can be precise and consistently wrong because it is describing sampling variability around the estimate, not correcting systematic errors. This matters in data AI because issues like sampling bias, data leakage, and measurement bias can distort estimates in ways that more data does not fix. An exam might describe a situation where the dataset is not representative and ask what happens to confidence or uncertainty as sample size grows. The interval might get narrower, but it narrows around the wrong center if bias is present. This is a powerful lesson. Precision is not the same as accuracy. Confidence intervals speak primarily about precision under a model, and you still need to consider whether the model and the data collection process are appropriate. Another common failure mode is reading a confidence interval as a guarantee that values outside the interval are impossible or extremely unlikely. The interval is not a boundary of reality. It is an uncertainty range for a parameter estimate given the method's properties. It is entirely possible for the true value to lie outside the interval in a particular sample, because even a 95% method fails about 5% of the time in the long run. Beginners sometimes treat the interval as a protective wall and say things like we are 95% sure the true value must be inside, using must language that is stronger than the concept supports. On an exam, the safest language is about compatibility and plausible ranges under the model assumptions, not about certainty. You can say the interval suggests the true value is likely within that range given the method, but you should avoid claims that imply absolute probability for the true value after seeing the data. This careful language is not pedantic. It reflects the correct underlying logic. Confidence intervals also play an important role in communicating results, and exams often test whether you can interpret what an interval implies for decision-making. A narrow interval that lies entirely in a range of practically meaningful benefit can support a decision to adopt a change. A narrow interval centered near zero may suggest any effect is too small to matter, even if it might be statistically detectable. A wide interval that spans both meaningful benefit and meaningful harm suggests uncertainty is too high to make a confident decision, which might motivate collecting more data or improving measurement. This is where confidence intervals become more useful than a single p-value, because they show magnitude and uncertainty together. In data AI, this matters when you evaluate whether a model improvement is real and meaningful or just noise. If the interval for improvement is wide, you should be cautious about claiming the model is better. The exam often rewards this kind of measured interpretation. A helpful way to avoid traps is to develop a consistent checklist for interpreting any confidence interval you see. First, identify what parameter the interval is about, like a mean, a proportion, a difference, or a ratio. Second, note the confidence level, because it reflects a trade-off between coverage and width. Third, interpret the width as precision and the center as the estimate, while remembering that precision does not fix bias. Fourth, if you are testing a claim of no effect, identify the no effect value and see whether the interval crosses it. Fifth, connect the interval to practical significance by asking whether the whole interval sits in a region that matters for decisions. This checklist can be done quickly, and it prevents most common misreads. It also keeps you from being tricked by answer choices that use confident language incorrectly. Confidence intervals reward careful thinkers, and careful thinkers can still be fast with a good habit. To wrap up, confidence intervals are one of the clearest tools for expressing uncertainty when you estimate something from data, but only if you interpret them correctly. You learn that the confidence level describes the long-run reliability of the method, not the probability that a single computed interval contains the true value. You learn that interval width reflects precision and is influenced by sample size, variability, and confidence level, with higher confidence usually producing wider intervals. You learn that intervals are about parameters, not individual observations, and that overlap between intervals is not a perfect significance rule. You also learn that confidence intervals do not protect you from bias, and that narrow intervals can still be centered on the wrong value if the data is systematically distorted. Most importantly, you build a way to connect intervals to real decisions by considering both magnitude and uncertainty, rather than relying on a single number. With these habits, you will be able to read confidence interval questions on the exam without falling into the classic traps that make this topic seem harder than it actually is.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.